Okay, welcome back. We are going over pages 7 and 8 from the Sequences in Series packet. This was kind of a tricky and interesting problem. Here we have take the entire plane, which is of course infinite, kind of in all directions, and let's divide the plane up into regions by dropping lines into the plane or something like that. Okay, so if you have one line, then that one line will divide the plane up into two regions. In fact, they're called half planes. There's the stuff on one side of the line and the stuff on the other side of the line. So already drawn here is what is also already drawn on your paper, which is that if there are I guess let's see what is this is the picture. Let Rn let's read it. Let Rn represent the number of regions formed when n lines are drawn in a plane such that no two are parallel and no three are concurrent. Okay, so this is R1. So how many regions do I get when one line is in the plane? Answer, 2. I don't even think I'm ready to think about this yet. Now, of course, now comes a second line. Well, I have to now read this a little bit more carefully. Of course, if I now, with my second line, if I make it parallel to the first line, okay, well then that's like not what you're supposed to do, right? If you have two lines that are parallel, then that will, in fact, divide the plane up into 3 regions. There's like the part in the middle and then the part on either side of the 2 lines. So that's not what we want. Therefore, I never want to draw lines that are parallel to previously drawn lines. So, okay, well, in other words, let's draw for my second picture, my second line in such a way that it intersects the first line. Okay, well here I think it's also kind of extremely obvious that the answer is you're going to get 4 regions. Duh, that's just like the 4 quadrants that you get from, any two lines intersecting. So therefore R2 is 4. And I'm just really not ready to even start understanding this problem yet. I'll just say one comment, which is, of course, no matter where, if the 2 lines are not parallel, then they must intersect. But they might not intersect like in my little zoomed in picture here. So actually what makes this problem hard is drawing your problem sufficiently general, because you don't want to draw the lines in such a way that they intersect like off your paper. Because if they intersect off your paper, then you're not going to be able to look at the picture. So of course, if we were doing this interactively, we would be able to sort of zoom out and zoom in and move around such that we could view all the relevant intersections. But here I'm sort of pre-drawing the boxes, and I need to be very, very careful when I draw the lines that all the intersections that are ever going to happen sort of like on my paper, so I don't kind of miss any. Okay, well now we finally maybe get to some real thinking. So what do we have now? Now we have 3 lines. Okay, so the question is, what is R3? This one was already drawn for you on your paper. Okay, here I am. Think of this recursively. In fact, the task here is to come up with a recursive formula. So, if we're thinking about this recursively, we should think about the 3rd line being sort of added to the already existing picture of the 4 regions determined by 2 lines. And now, note that once again, I'm not allowed to draw my 3rd line parallel to either of these, but I also can't draw my 3rd line in such a way that it goes through the intersection point of the previous 2 lines. So that's what we mean when we say no 3 are concurrent. So don't draw your lines ever so that the new line that you just drew goes through a point of intersection that already exists. In other words, don't have any 3 lines meeting at a point. Okay, so now what I need to do is I kind of need to cut through I need to cut through sort of as many lines as possible, but not going through that point of intersection that already exists and not being parallel. Well, great. So no matter where I draw the line, it doesn't really matter. But if I want to draw it on my board or on my paper such that I can see what's going on, I should let the points of intersection be pretty close to this kind of general zoomed in area. And okay, well look, there are only 2 lines. So can I make a Yeah, so where will my third line go? Well, no matter where I draw it, it's just going to intersect, both of those two lines, because duh, it can't be parallel to either of them, and it can't go through their point of intersection. So that's that. It's going to intersect kind of both of them. Okay, well, if it intersects both of those lines, then here's an example of what that line can do. It can look like this. Now, I think there's nothing special about putting it up here. I could just as well have put it down here. But now I'm starting to kind of see what's going on. And if you see what I did, I sort of added this new line to this figure, like chuk, 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 chuk. And what does it do? Well, one of the regions, namely this one, is left kind of like preserved. I'm not sure how to kind of mark this. Maybe I'll put a sort of red dot here and a red dot here. Though these pictures are looking a little bit off from each other, that is sort of a pristine region. It doesn't get affected, right? In the situation with just 2 lines and the situation with just 3 lines, that region remains unchanged. And that's because I drew my third line in such a way that it intersects sort of a particular kind of 2 rays of the 2 lines that already exist. And this gives some kind of insight into what's going on, right? Because what do I essentially do? By this line cutting through these 2 lines, this region gets cut in half, this region gets cut in half, and this region gets cut in half. And so this single region becomes 2 regions, this region becomes 2 regions, and this region becomes 2 regions. And that's what I've drawn here. Okay, that was the end of the... Oh, and so the answer is, well, you can just count, right? The answer is 7. So 1, 2, 3, 4, 5, 6, 7. Okay, so R3 is 7. Great. Now you have to start doing things yourself. And now it started getting hard. So I have... Oh, okay, I already drew it in. So I need to now drop in my 4th line. How am I going to draw this 4th line? Well, if this 4th line is going to be, there are already 3 lines that exist, the 4th line is going to be not parallel to any of them, and therefore it is going to intersect all of them. So in any given, in each step, as I go from the 3rd step to the 4th step, and I go to draw my 4th line, that 4th line is in fact going to have a point of intersection with each of the 3 previous lines. So I need to draw my line in such a way that it cuts all 3 of the lines from the previous step. And actually, as I said, the hard part is making it cut all 3 of those lines and still sort of staying, having it do it sort of on the paper and not kind of off the paper. Okay, so that's what I've done here. I point with my finger to this 4th line, which indeed 1, 2, 3 meets those 3 lines. And I guess I can just kind of start drawing these in now. But okay, let's draw them in. This will take a minute, so relax. Let me try to do sort of a fast job. Well, okay, so once I decide to color one region, then the rest are determined. Right? Am I crazy? No, I'm not crazy. So, and there's probably a lot of different ways of doing this problem. So maybe this is just kind of one way of talking this out. Yeah, I mean, I don't think I've ever gone over this problem actually during class. So I've never heard from what other people have to say. Anyway, okay, let's try to wrap this up. Alright, let's discuss again the kind of pristine region concept from the last from the previous step. I think now I have several kind of pristine regions which don't get touched. Well, okay, this is sort of the nature of it, right? When I go to when I go to cut all 3 of these lines, which I do, right, forming these kinds of 3 new points of intersection. What are the 3 new points of intersection? Sort of this one, and this one. So what should I think about these 3 new points of intersection? Well, they are going to cut some regions in half, creating new regions. But how many new regions are created? Well, I think what you need to appreciate is that some regions are totally unaffected by this cut. In particular, now, this region is unaffected. This region is unaffected. This region is unaffected. This region is unaffected. Is that it? I'm probably missing one. No, that's probably it, right? Because let's see, 1, 2, 3. Yeah. So there should be. Oh my gosh. Maybe this is the wrong way to put it. Let me draw the regions which are unaffected on this picture. And the answer is it's all these, right? So 1, 2, 3, 4. Yeah, so okay, so this is kind of the big idea here, right? So in the transition from this figure to this figure, what am I going to do? I'll tell you what I'm going to do. I am going to cut, I'm going to add a new line, in fact I already did it, which cuts through the 3 previous lines. Well, it's going to cut through those 3 previous lines in 3 different places. That's the 3 black dots. But by cutting through those 3 lines, you should think of those, okay. Well, okay, these 3 regions are going to be just unaffected by that new line. And that's because the line is really sort of cutting through 3 rays, and that many rays are only going to make 4 regions. Alright, what the hell am I talking about? Let me try to explain. I think I had it better a little bit before, in my mind, a little bit before this video started. Okay, 1 line creates 2 regions. 2 lines create 4 regions, but really we should sort of be ignoring kind of the region that's unaffected. Because this line, so I guess it's like this, right? When I added the 3rd line to this second picture, this line can't cut through sort of all of the regions. It can only cut through some of the regions. And specifically, it's going to cut, it did cut these 2 lines kind of like here and here, right? And so, when I cut through I'm only going to affect sort of 3 regions. So only this region, and this region are affected by this addition of the 3rd line. And so those 3 regions get cut in half. Thus we create 3 new regions. Okay. Now, in the transition from this step to this step, I add these 3 new points of intersection. But those 3 new points of intersection are going, the act of cutting through 3 lines creates 4 new regions. Which is to say that these 3 regions remain unaffected. And I'm searching for like a very convincing proof of this fact, but of course you can just kind of see it, right? That it's this region, this region, this region, and this region are going to get cut in half. That's in fact exactly what happens, right? This big region becomes this one and that little one. This little region becomes this little one and that one. This big region becomes this one and that one. And this region becomes this one and that one. So okay, so what I need to sort of convince you of, or possibly just move on, is that a line, when this line cuts through 3 previous lines, precisely 4 regions of this figure are going to be affected and are going to be cut in half. And I guess the reason why that is, maybe I'm just gonna sort of leave it and then just take that as kind of an observation. Yeah, it's because a line, this new intersecting line, can only cut through a line at a certain kind of place. So it can't affect, it's like this. This is actually quite complicated to articulate precisely, but this new line is coming in like this, right? And it's this new line, give or take. It's this blue line I've just drawn, which, give or take, is going to be the line that I'm about to draw in the next step. In fact, I did it already. Okay, well, let's talk about this line. It's this blue line. It's going to form these points of intersection here, here, and here, right? But upon doing that, Okay. If it can't affect regions formed like completely away from that line. So if I look at these 3 points, right? It's going to intersect the 3 previous lines. Call this line. Let's see. This is the first line I drew, so that's L1. This is kind of spiraling out of control a little bit. This is line L2, and this here is line L3, because that's the order in which those lines were drawn. Well, this point, call it P1. This point, call it P3, and this point, call it P2. What can I say about them? Well, this point P1 is on one sort of side of I think I will give up. But basically, these 3 regions in red dots are not affected by the addition of this blue line, because they are regions formed by points which are fully on the other side of that blue line I just added. So any points, any regions which are created by points which are all in the other half don't get changed at all. If this line cuts through part of the region, then so be it. Okay, so I guess I've just wasted 5 minutes of your life, but essentially what I need to convince you of is that this blue line cuts through 4 regions, and okay, it certainly just does. And since it cuts through 4 regions, 4 regions are going to get cut in half, and that's why I add 4 regions. So I don't even need to count. I can just tell you right now that R4 is going to be 11. This gives me a way to sort of finish this off now, because here I've just now copied the exact same diagram over again. And what I'm about to do is add my 5th line. Well, alright, if I understand what's about to happen, when I draw my 5th line, it's going to intersect each of the 4 previous lines. And by intersecting each of the 4 previous lines, it's going to cut through 5 different regions. And the 5, so I'm about to draw this line now. Here's what it's going to do. It's going to go there, like that. And so it's going to intersect here, 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 and here. But regions which are entirely formed by points of intersection on the other side of this new line I just drew. So this region is going to be unaffected. This region is going to be unaffected. This region is going to be unaffected. I see now that my explanation is not totally general, because this region is also going to be unaffected. And I guess in general, oh man, what's it going to be? I'm adding 5, so 6 regions are going to be unaffected. And those 6 are, yeah, well, it's pretty clear, right? It's these 6, I guess. These are the 6 regions that are going to be totally unaffected. Although I'm not giving a very good geometric proof of why that is, but it's certainly true that 6 regions are going to be unaffected, but the remaining 5 regions are all going to be affected. And so this 5th line, when I draw this 5th line, I cut 5 different regions in half. I cut this region in half, this region in half, this region in half, this region in half, and this region in half. And therefore, I just added 5 new regions. And so R5 is 16. Okay, and in general, I'll just tell you now, I've determined the pattern, that the nth line is going to have the same number of, or the plane divided with n lines, not parallel or all 3 meeting in a point, is going to have the same number of regions as the previous step plus n. Okay, this was the entire thing, and you didn't even really need to give a proof of this or a justification. You just had to kind of make this observation, which is perhaps as far as I ever got when I did this before. I'll just say that it's also possible to give an explicit formula for this, because what does this thing look like? Well, what is this sequence anyway? It's 2, 4, 7, 11, 16, etc. So what does this sequence look like? This sequence is just adding, I'm adding 2, then I'm adding 3, then I'm adding 4, then I'm adding 5, etc. So what is this sequence like that adds 2, then adds 3, then adds 4, then adds 5? Well, this sounds kind of like the triangular numbers. After all, the triangular numbers that we've already seen, right? There's 1, then you add 2, then you add 3, then you add 4, and we both have experienced these and understand them and know the formula for them. This is the sum of the first 1 numbers, that's 1. This is the sum of the first 2 numbers, that's 3. The sum of the first 3 numbers, that's 6. The sum of the first 4 numbers, that's 10. Well, our sequence here is almost that, right? It's like start with 2, but then to get to the next one, add 2. So it's like this. Then to get to the next one, add 3. Then, to get to the next one, add 4. So what is this? You can say that this is basically the triangular numbers with one kind of extra thing, you know, that's triangle, 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 with one extra point, just kind of extra. Okay, and therefore, I can just tell you, based on this observation, that the formula here for Rn, the explicit formula for it, is going to be 1 more than the nth triangular number. So it's going to be 1 plus n plus 1 over 2. And that is actually just the correct formula, and you can check to see that it works for all the numbers that we've seen so far. And by the way, there's even another way to get this explicit formula, and it's actually the way I did because I was being kind of dumb, which is to observe that sort of what kinds of numbers, you know, go to 2, 4, 7, 11, 16. I like this a little bit because it connects to some other things that we were doing. So what are we doing? We're going up by 2, we're going up by 3, we're going up by 4, and we're going up by 5. So what kind of function increases at a linear rate? Or rather, I should say, what kind of function has finite differences which are themselves arithmetic? And the answer is quadratic functions. So based on everything you learned last year and what we did in this class kind of recently, I can say that this 2, 4, 7, 11, 16 must be some kind of quadratic function, because it is precisely quadratic functions which increase at a linear rate, and this is linear. Therefore, if you wanted to, if you didn't trust this formula, or if you wanted to discover it yourself, you could just set up a little equation and just be like, all right, when I plug in when I plug in 1, I get 2. So, you know, A plus B plus C is 2, because the first number outputs 2. And then, you know, when I plug in 2, I get 4. So 4A plus 2B plus C is 4. And when I plug in 3, I get 7. So 9A plus 3B plus C equals 7. Okay, and therefore, once you know it's a quadratic and you have some data, you can sort of solve the system of equations to find out what A, B, and C are, and you will actually get this. All right, that was extremely long. I might even like tell you not to watch this, and everything is great except for I'm very dissatisfied with my justification, which is going to involve some sort of low-level geometry argument. But the claim that I'm making is that when you draw your nth line, the nth line that you draw must necessarily cut through n previously existing regions. And maybe it's just an extremely simple thing, like, yeah, maybe it's just an extremely simple fact, right? The nth line must cut through precisely n regions. Yeah, it's just true, but I can't articulate any more sort of why. I can say some more kind of stupid things, but that's all I got. Okay, good. There's like more to this packet, so I think I'll finish this later. Okay, we're back. This is a more straightforward, kind of simple problem. Find the sum of all the positive odd numbers that are divisible by 5. Okay, well, yeah. Positive, we're looking at positive numbers only, odd numbers only, and divisible by 5 only. Well, 5 is divisible by 5. What's the next multiple of 5? 10, but that's not odd. So basically, we're looking at like 5, 15, wait, there must be, sorry, positive odd numbers less than 400, there we go, which are divisible by 5. So 5, 15, 25, etc. Those are just the numbers which are both multiples of 5 and also odd. Yeah, so any number which is like, 5 more than a multiple of 10, basically. The numbers which are multiples of 5 but not multiples of 10. Okay, so, well, there it is. Then what's the last one? 395. So now this just reduces to, hey, what is 5 plus 15 plus 25 all the way up to 395? And, well, I guess I can just kind of do this, right? If I call this the first term, then, and I call this the nth term, then what's the formula for my nth term in general? It's just going to be the first term plus a whole bunch of d's. What is d? D is 10 in this case. And so I have to add 10, n minus 1 times to get to the nth term. And so this is 395, this is 5, and this is 10 n minus 1. This is one way of doing this. And so then this is 390 equals 10 n minus 1. And so 39 is n minus 1, and so n is 40. I bet it was also possible to just do this whole thing in your head by just kind of being smart or something, and saying, okay, so from 5 to 395, what do I have to do? I have to advance 39 times by 10. The gap is 390, and so therefore I did 39 jumps of 10 each. So if I did 39 jumps, then this is the 40th term. That's just kind of do it in your head style. Okay, but anyway, that is the 40th term. Now that I know it's the 40th term, how do I, now I just apply the formula, and yeah, I mean, here I'm tempted to say that it's just that the formula for the sum in the first instance, so there are multiple versions of it. There's n 2a plus n minus 1 d over 2. That's like the real formula. But then this is also just the first term plus the last term over 2. Because it's arithmetic and everything sort of balances, you're really taking sort of the average of the first and last term multiplied by the number of terms. So this might seem to be easier or something, right? Because this is the 40th term, so I have 40 terms altogether, and the average of the first one and the last one is just 200, right? Yeah. So, cha-cha, and therefore this sum is 8,000. Okay, then there are other ways to do it. You could just plug all the numbers into this formula. You could even, okay, that's good enough. Alright, 29, this is a cute little problem, which I think initially I did this like not the good way. So plus 5, minus 7, plus 9, minus 11, and then all the way out to plus 1001. Okay, and the question is, what is this? Alright, so there are two ways to do this bit. There's a couple ways to do this. One thing you could do is you could collect all the positive terms together, collect all the negative terms together, and kind of sum them all up, sort of how we did here. But actually, there's something a little bit more interesting going on, which is, let's see, the smoothest way to do this is plus. Okay, so it ends with a plus. So, yeah. So watch, we're going to do it like this. We're going to think of this as 1 plus, and then in parentheses we'll write -3 plus 5. And then we're going to say, okay, what's next? -7 plus 9. What's next? -11 plus, okay, and what can be seen by grouping is that all of these are just 2. So that's 2, that's 2, that's 2, etc. And because we end with a plus, it must be that this last one is -999 plus 1,000. 1,001. So that's 2. What is the real answer to this problem? It's 1 plus a bunch of 2's. How many 2's are there? Well, 1,001 minus 1 is just 500, is 1,000. So there are 500 of these pairs. Oh no, actually, sorry, that's not right, because these numbers are also skipping by 1 every time. So I guess there are 250 of these things in parentheses. Yeah. Okay, so that's 1 plus, there are 250 of these 2's, and that's just 501. I think this is the kind of middle school math team, I'm so smart, kind of way to do this problem, to really to group and think of it as a sum of a bunch of 2's, or potentially a sum of a bunch of negative 2's, if you don't want to put one by itself. But you could also do it in a more sort of traditional way, where you do like 1 plus 5, plus 9, all the way up to, 1,001, and then minus 3 plus 7. This is kind of a little bit more lame way to do it. Plus 999. And what you will find is that this is an arithmetic series which is skipping by 4 every time. And this is actually what I did. I got that this was well, never mind. The answer to this problem is 501. Okay, good. Time is it? Really want to finish this, but I don't think I can. Okay, stopping again. Okay, finishing up, yikes, this page 8 of this packet. Okay, let's go. Here's number 30. Here's what it says. If you go back through 10 generations, how many ancestors do you have? Okay, so you've all seen this sort of thing before, where you make a family tree or whatever, and okay, here's you, and let's just say you have, your 2 parents or whatever, and then your 2 parents have 2 parents, and that's grandparents, and okay, if you're, very fancy, you can learn all your 8 great grandparents, and etc., etc. So it seems as if we have a geometrically increasing number of total ancestors. Okay. What the first question says, if you go back through 10 generations, how many ancestors you have? Okay, well, and then if the packet clarifies, count your parents as the first generation, your 4 grandparents as the second generation, etc. I don't know why I did it this way. So let's not count you. You're not your own ancestor or something like that. So it seems that we're just adding 2 and 4 and whatever. So okay, so this is going to be 2 plus 4 plus 8 plus, and we have to be a little bit careful, right? Because we're adding 10 terms, because we want to count 10 generations, and so this is like 2 to the 1, 2 to the 2, 2 to the 3, so this is like 2 to the 10th. Okay, so, okay, fine. So if I want to use the formula for the sum of a geometric series, I just need to be a little bit careful, because the formula says, a times 1 minus r over to the n over 1 minus r, So here, all right, I have, what am I trying to say? Well, maybe there's nothing to say. The first term r to the n over 1s r. So we're adding the first 10 terms of this series. So it's going to be 2 times 1 minus 2 to the 10th over 1 minus 2. Okay, and so what is this? This is just going to be 2 times 2 to the 10th minus 1. And what is that? 2 to the 10th. I kind of just know that one by heart. That's just 1024. So this is just 1024 minus 1. And so this is 2 times 1023. And so the answer to this is 2046. Okay, follow-up question. How many generations must you go back in order to have more than 1 million ancestors? Okay, so in other words, when is 2 plus 4 plus 8 plus all the way up to n, so that's 2 to the nth, when is that going to be bigger than, what did I say, 1 million? Yeah, 1 million. Okay, well, I guess we can just do this, right? What is the sum? Well, we just kind of did it over here. It's 2 times 1 minus 2 to the n over 1 minus 2. So when is that bigger than a million? Chop, chop. Okay, well, what do we have here? Well, let's sort of divide by 2. So that's like saying 2 to the n minus 1 has to be bigger than 500,000. And so when is 2 to the n bigger than 500,001? Okay, this is just right, everything I just put here, but it is a little bit, oh yikes, it is a little bit misleading or something maybe. Okay, sorry, not misleading. This is a little bit just fine, everything's fine. And you want to now solve this. So I bet you're tempted to reach for your calculator at this point, but okay, if you want to be super like smooth and know all the powers of 2, multiply both sides of this by 2. And so what we really want is like 2 to the n plus 1. When is that bigger than 1,000,002? Why would I do such a thing? Because I happen to know that 1,000,000 is like, roughly speaking, you know, okay, 1,000,000 is of course 1,000 squared. That's just true. So 1,024 squared is like very, very close to 1,000,000. And 1,024 is 2 to the 10th. And therefore, 2 to the 20th is very, very close to 1,000,000. So that's just like a nice little fact. In fact, yeah, 1,024 is like a kilobyte, actually, and I guess this is like a megabyte. So a megabyte is not really 1,000,000 bytes. A megabyte is like, I don't really know what I'm talking about. I think this is true. It's, because it's all in binary, it's like 2 to the 20th. Okay, therefore, when is, so let me now make sure that I do this right. This will be, so instead of figuring out when this is bigger than 1,000,000, I'll say when is this bigger than 2 to the 20th, which is just slightly more than 1,000,000. So if you're bigger than 2 to the 20th, you will be bigger than 1,000,000. And therefore, the answer to this is 20. So I think 19 will be good enough. Okay, I guess what I'm really doing is like that, if we're being super careful, right? I'm bigger than 1,000,002 if I'm greater than or equal to 2 to the 20th, since 2 to the 20th is slightly more than 1,000,002. Okay, or you can just do some stuff with logarithms in your calculator and you will get the answer 19. Okay, well, this is pretty interesting. And in fact, what this suggests is if you go back 19 generations, you will have like 1,000,000 ancestors. Well, that's a very big number, but okay, there could be 1,000,000 people in the world. Well, go back like 30 generations. Now how many are there? Well, 2 to the 30th. Now we're talking about numbers that are like, you know, billions in the tens of billions. We don't have tens of billions of people. So what is the answer to the mystery? When I go over this problem in class, I now ask the question, how could it be that the further back in time you go, the number of ancestors just keeps growing and growing when, in fact, we know that there were only like, say, 500 million people, you know, in the entire world as recently as like 150 years ago. That might be right. And the answer is to this paradox of the farther back in time you go, the more people there are in the world, is inbreeding. You do not actually have, you might have 8, you better have 8 distinct great-grandparents, but beyond that, it's like, man, who knows? It's very possible, and in fact necessary, that when you go back, say, 5 or 6 generations, a lot of these people are not actually different people. You know, which is to say, you know, your parents might be like 8th cousins or something like that. That's very, very likely. And in a small country, Ireland or something like that, you know, all those people are related to each other. People are just marrying their 3rd cousins, 4th cousins, 5th cousins all the time. Okay, good. Let's just, taking me forever to go over this packet. Let's just finish this up. Last 2 problems, which are just math problems, so there's nothing to really like talk about. 31. The sum of an infinite number of terms of a geometric sequence is 15, and the sum of their squares is 45. Find the first 5 terms of this sequence. Okay, I've been assigning this problem for 10 years. People find this problem pretty hard, actually, and part of it is because the description of the problem is just given to you verbally, and so you have to sort of choose your own variables and things like that. So you have to be sort of confident enough to read these words and say, okay, the sum of an infinite number of terms of a geometric sequence is 15. Alright, well that must mean that, you know, a plus ar plus ar squared, you know, forever, is going to be 15. In other words, have enough confidence to express a generic geometric sequence in terms of the first term and in terms of the common ratio. And this is what we're being told. That if you add up all these terms, you get 15. Okay, the sum of their squares is 45. Okay, so if I add up the squares of all the terms of this series, that's 45. Okay, well, what's a squared? Well, it's just a squared. What's ar squared? It's ar times ar, so that's a squared r squared. What's ar squared? It's a squared r to the 4th. Maybe I want to throw in even like one more of these, because this is ar cubed. And then this becomes, therefore, when you square it, a squared r to the 6th. Okay, so I'm squaring every single one of these terms. And when I do that, I get 45. Okay, well, pretty interesting. And actually, that is sort of all the thinking that really is required in this problem, or all the sort of deep thinking. Now, maybe we just do some algebra and sort of formula application. Let's see, what can I do with this? Well, one thing I can do is I can use the formula for the sum of the terms of a geometric sequence. What is this 15? This 15 has to be a over 1 minus r. And what about this? Well, it's perhaps not totally obvious immediately, but this is also geometric, right? What are we doing? We're multiplying by r squared, we're multiplying by r squared, we're multiplying by r squared, etc. And okay, if I keep multiplying, so this is geometric. Therefore, I can represent this sum as the first term, a squared, over 1 minus r, which is r squared. Okay, so having done all that, now I think I really do have simply an algebra problem on my hands. This all just boils down to, I got two equations in two variables, and now you have to either find a good way or a bad way or some kind of way to solve this system of equations. And alright, depending on your sort of luck or experience, you might just do this problem now in 1 minute, or you might get totally stuck here. Anyway, I'm going to help. One thing we can do is get rid of fractions. That always just seems like a good idea. So if I get rid of fractions, then this is saying 15a equals 1 minus r. And this is saying 40, sorry, that's wrong. 15 times 1 minus r is a. And this is saying that 45 times 1 minus r squared is a squared. Okay, there are so many things we could do now. I don't know. We could, I mean, one thing we could do, there's so many things we could do. We could just stick a, I mean, maybe the simplest thing to do is just do this, right? Just stick this in here, and then be done with it, right? Because then we just have a single. Let's just do that. That's not the smoothest, coolest way to do it, but it is like a way. And in fact, this 1 minus r squared, this is like 1 minus r, 1 plus r, and when you square, if a is just 15 times 1 minus r, then if we put this in here, this becomes 15 squared, 1 minus r squared. Okay, and now I have just a single equation to solve, and yeah, let's just do it. Well, I can divide both sides by 1 minus r, leaving me, and I can also, 15 squared is like 5 times 3 times 5 times 3, and this is 5 times 3 times 3, so that leaves me with just a 5 on the right-hand side. I think I did that right? Yeah, so this becomes 1 plus r equals 5 times 1 minus r. Sorry, that was a little bit badly explained. I canceled, just one of these, ka-cha, and I basically divided both sides by 1 minus r, and I divided both sides by 45. And 45 is just 3 times 3 times 5. So this is 3 times 3 times 5 times 5. So that leaves me with 5 left over. Okay, well, now this is just legit Algebra 1. Yeah, this is like the best way. I think this is better than whatever I was going to do. Equals 5r, and so I guess I get 6r equals 4. And then that means r must be 2/3. Yeah, that's just like right. And if r is 2/3, then 15 equals, then 1 minus r is 1/3, so 15 times 1/3 has to be a, and so a is 5. Alright, so actually you just really had to understand the problem, verbally sort of decompose the language, pick variables for the things that you don't know, observe that the squares of a geometric sequence also form a geometric sequence, so therefore that this is a geometric series, apply the formulas, and then just do a little bit of algebra to solve this system of equations. And then what's the final thing I'm supposed to do? I'm supposed to write out the first 5 terms. So I guess the first term is 5, and then the next term is 5 times 2/3. This is a little bit dumb. And then 5 times 2/3 squared, 5 times 2/3 to cubed, and 5 times 2/3 to the 4th. That'll be the first 5 terms. Okay. Oh man. Finally done with this. Number 32. In an arithmetic sequence of complex numbers. Okay, so this is already just crazy. I'm suddenly just back on the complex numbers. What's up with that? Don't worry about it too much. Here's what I'm told. I have a sequence of complex numbers, and it's an arithmetic sequence. Well, what's an arithmetic sequence of complex numbers? I guess it's just the same thing. It's a sequence in which the differences between a term and the previous term are constant. Okay, find the next 3 terms of the sequence, find the 25th term, and find the sum of the first 25 terms. Okay, well, what is the, well, what did it say? Find the next, okay. Yeah, so what is the common difference? The common difference is just going to be 3 plus 4i minus 1 plus 3i. In other words, the common difference is 2 minus I. No, plus I. Yeah, great. So what is this sequence doing? You're just adding 2 plus I every time. And therefore what this sequence looks like, 1 plus 3i, comma, 3 plus 4i, comma, 5 plus 5i. Is that true? Yeah. 5i, comma, 7 plus 6i, comma, 8 plus 7i. I hope I did that right. No, I messed up. 5, so this would be 9. Okay. Yeah, so in some ways it's like, it's an arithmetic sequence of complex numbers. It's like 2 arithmetic sequences kind of combined or something like that. The real parts are forming an arithmetic sequence with d equals 2, and the complex parts are forming an arithmetic sequence with d equals 1. Okay, well, what's the 25th term? The 25th term is just going to be the first term, so 1 plus 3i plus 24 of these d's. So it's really just that. And I guess what do I get? 48 and 1, and that's 24 plus 27i. Okay, great. Final thing, what if I want to add a whole bunch of these? Well, I don't see any reason to suspect that I can't just do the same normal things with this, because that's just, complex numbers are just kind of like pairs of real numbers. So this is going to be 25 halves. I should rewrite the formula. I want the sum of the first 25 terms. So what's the sum of the first n terms of an arithmetic sequence? N over 2 times 2a plus n minus 1d. I just know that formula by heart. So if I want the sum of the first 25 terms here, then that's 25 over 2 times twice the first term, which is 1 plus 3i, plus 24 of those d things, which are 2 plus I. And then I guess I just do this out, right? So what is that? 25 halves times, that's 48 and 2 is 50. And then that's 24 and 5 is 29. That's not what I was expecting to happen. What? 24 and 6 is 30. There we go. Great. You could, well, okay, that just works fine, I suppose. And you could also have just taken the average of the first and the last term. That would have been even easier. So what do we end up with here? Big numbers. I guess this is like 625. Yeah, because it's 25 times 25. And then it's 25 times 15, which is 375i. Okay, goodbye.